Hi, thanks for being here. I'm going to present some joint work with Sander Gribbeling from Tilburg University. Let me just put a timer down. Okay, so I'm going to talk about quantum speedups for linear programs via interior point methods. The talk kind of broadly splits up into some background on LPs and IPMs. Then I'll talk about how we approximate Hessians, gradients, and how we combine these things into forming a quantum LP solver. So LPs and IPMs. I'm sure most of you are familiar with this picture, which represents some polytope defined by a set of constraints. There are some linear functions that we want to optimize, and we can find this optimal point inside the corner of this polytope. So in maths, we write this down as minimizing this linear function C transpose X, where X is constrained by a set of linear constraints, which we combine into a large matrix AX, larger than or equal to B, element-wise. Right? So each of these faces of the polytope represents one particular linear constraint. Throughout this talk and this work, we're going to assume the setting where the number of constraints is much larger than the number of dimensions. Okay, so you want to think about D, number of dimensions, is kind of relatively small, but then there's a large number of constraints. Okay, so like in this picture, this is a two-dimensional polytope, but there's 1, 2, 6 constraints. Okay, but in general, N will be asymptotically larger than D. This is one of the canonical examples of convex optimization, more specifically of constrained convex optimization. So somehow this connects a little bit with Stephen's question from before. What if you impose some constraints to your convex optimization problem? Why do I mention this? Because typically we don't like so much constrained problems. We prefer unconstrained problems. And there is a way of turning a constrained convex optimization problem into an unconstrained one by somehow putting these constraints into the objective function. Okay, and typically we do this using this notion of, at least in interior point methods, we use this notion of a barrier function, which is a function that goes to infinity as we approach the boundary of the polytope. Right, so it looks a bit like this, where level sets kind of start, accumulating around the border, and this function goes to infinity as we approach the border of this polytope. And now we can do the following. Okay, maybe one example that'll kind of show up a couple times more is the logarithmic barrier or log barrier, which is essentially the sum minus the sum of the log of the slacks. So AI transpose X should be bigger or larger than or equal to BI. So somehow this represents how much space do we have left, with respect to this constraint. And this blows up as we approach the boundary, as this constraint starts going to be satisfied or gets tight. So this is a log barrier. It'll show up a couple more times. And now we can consider the following problem, which is we minimize a new objective, which is the linear objective plus this barrier function. Okay. And this results in an unconstrained convex optimization problem now, which we like much more because now we have a smooth objective function and we're unconstrained. Okay. And in fact, if you choose your F appropriately, you can ensure that the minimizer of this new function we want to optimize sort of approximates the minimizer of the original LP, right? Remember that in the original LP, the opt was in this corner, and now we get some opt prime. It's kind of close to that as we choose f of x appropriately. So what does it mean choosing f of x appropriately? One particular way of thinking about it is taking this parameterized function f eta of x, where we have the barrier function. We don't change that, but we sort of put a parameter in front of our linear objective. And somehow intuitively, as we make eta larger, this linear objective becomes more important, and we're going to squish this opt prime closer to the actual opt, closer to the actual corner of the polytope. Precisely what we can do is we can define this notion of a central path, which is a curve of points z eta, where z eta is a minimizer of f eta. Okay, and this forms a continuous path. This is what we call the central path. And as eta goes from 0 to infinity, somehow this traces out a path from some center of the polytope in a certain sense to opt. Okay, and this also directly suggests a way of getting towards opt. And since I guess you're all mostly quantum people, you can think about this as somehow following an adiabatic path if you want. This is precisely the idea of path following, where we assume that Z0, right, this sort of center of the polytope, which doesn't take into account the linear function that we want to optimize, is easy to prepare. So we start from that point, and then we want to kind of trace along this central path until we get to the true optimizer. And how do we do that? We use this notion of Newton steps. More specifically, path following is the following idea. We start from some small but non-zero eta, right? So that if we start in this point, we're kind of close to the optimizer, and then we increase eta, so that the new minimizer kind of moves along the central path. And then we implement a Newton step. So we update our x to a new point, and we implement a Newton step with respect to the function f eta. Okay, so this Newton step is very important throughout this talk. It takes the following form, right? We start from some point x, and we're going to subtract the inverse of the Hessian multiplied with the gradient. Okay, so this is a Hessian matrix of second derivatives, and here's the gradient of this function f eta. Good. So how do these Hessians and gradients, what kind of form do they take? Let's look at the logarithmic barrier again. I already introduced this notion of slack, so which kind of measures how close are we to this particular face of the polytope. Right? AI transpose x minus bi, and f of x just minus some of the logs of this thing. What's not hard to see is that if you compute the Hessian of this, it actually takes the following form. It takes the form of like this B transpose is just a rescaling of A transpose. B is a rescaling of A. So essentially what you get is you get this sum of outer products of the constraints. So H is a D by D matrix, right? Recall that D is relatively small and is very large. So this is a large sum over kind of small D by D matrices. So we have many constraints. And this 1 over SI squared somehow singles out the constraints that are more important, right? If the slack is small, then this is a more important constraint at this point in time. So this is what the Hessian looks like, and the gradient takes a somewhat similar form, is minus, again, this B transpose times the all ones vector. Okay, so again, this is a relatively small vector, d-dimensional vector, but is a result of taking these sort of d large n-dimensional inner products. Okay, so this form will be important and will pop up again later. Good, that being said, let's go back to this idea of path following. So we want to do iteratively update eta and take a Newton step, right? So the first question is how many steps do you have to take, right? How many of these sort of green steps do you have to take to approximate the actual optimizer? And this depends on the choice of barrier. I mentioned this log barrier, but there's also more advanced barriers such as the volumetric barrier and a much more recent one which is called the Lewis-Wade or Lee-Sidford barrier. And what you can see is these barriers are more advanced in the sense that the number of increase that you have to do to get epsilon close, let's say, first scales as square root n, then as square root n, you find a square root d, right? And again, d is small, so that's good. We want that. That's the number of steps you have to take, but then somehow by kind of considering this increasingly complicated barrier, we pay a price for that, right? How do we pay a price for that? The price is in the single step that we have to implement. A single Newton step requires us to compute this inverse Hessian and gradient of the barrier. So if we take more complicated barriers, this is going to be a more costly step, right? So there's a bit of a trade-off there. In fact, you can argue that the log barrier kind of requires essentially matrix inversion. This volumetric barrier requires matrix inversion and the computation of a notion called leverage course. I'll explain what these are later on. And finally, this most recent barrier uses matrix inversion and Lewis-Wade, which is kind of a generalization of leverage course. Again, more complicated. Building on these ideas, the classical state of the art is a work by Van den Brand, Lee, Sidford, and Song from 20, where they show that they can solve these tall linear programs, right, where n is much larger than d, so the regime we're interested in, in runtime n d plus d cubed. Okay, but again, we're in this regime where n is much, much larger than d. So in some sense, this is the greatest of all time, right? This is linear in the input size. At least classically, you can't expect to do any better than that. They use this notion of IPM, path following, and combine that with some clever use of dynamic data structures. There's also prior work, quantum now, and most of the prior work, and also our work, focuses not on sort of changing the path following idea, but sort of speeding up this Newton step, right, where you have to do some matrix inversion. If you think matrix inversion and quantum, kind of come up with the following idea, which Kernides and Prakash worked out in 18, which is use quantum linear system solving plus tomography to estimate this vector here, right? There's a bunch of follow-ups, and there's also, I just mentioned for completing, some non-interior point method papers for solving LPs that I won't go into. So, I mean, this seems great, but of course, when you think about quantum linear system solving, the first thing that sort of comes to mind is the fact that there's this condition number popping up, right? We have to invert this Hessian here, but this is the Hessian of a function that somehow becomes more and more skewed as we get closer to the barrier, right? So as x goes to the optimizer, this condition number blows up, and all these methods depends on condition number. These methods based on interior point methods, and that's a bit unfortunate because that means that these methods are incomparable to the classical methods, and it's very hard to bound this condition number, right? So I would say that that's one of the main contributions of our work, is that we avoid this dependence on condition number. So what do? We again find this quantum speeder for the Newton step, but we use a slightly different idea. What we do is we kind of approximate this polytope, or more precisely approximate the Hessian explicitly by some easier to construct object, and then we use that to approximate the gradient. And this is going to be the two steps that I'll describe later on. What this gives us is a quantum algorithm for solving LPs whose runtime scales as square root n, right? This compares to n classically, times some poly d times log 1 over epsilon. So it's a high precision thing. It's sublinear in the regime that we're considering, and there's no condition number popping up. Okay. The greatest of all time in the quantum case, what can we say about that? There is this omega square root n d lower bound in terms of row queries. So row queries means how many constraints do I have to query? Okay, kind of show it's not too hard to prove you need something like square root n d row queries. So we get the correct square root n dependency, and there's still plenty of work to get this poly d down. So let's get into the details. All of this starts with approximating the Hessian. Good. So in a picture, it looks like this. We have this polytope with many faces, right? And we want to approximate it by a polytope that has fewer faces. Okay. And we're going to do that through the idea of constraint sampling, right? Consider this big constraint matrix, right? There's n constraints, where n is much larger than d. But all of these constraints are in a relatively small d-dimensional space, right? So many of them will kind of look similar, right? You have these sort of zigzagged ones, you have the block ones, you have some. And what we're going to do is we're going to try to somehow sample representative constraints and use these and put these in an A tilde, and this will be this orange polytope. Okay, so that seems great, but how do you make that work? So what you can show is just by sort of reverse engineering, we look at what kind of approximation can we afford on the Newton step. And it turns out that we can use a H tilde that spectrally approximates H. So we're going to take this A tilde, not so that A and A tilde kind of approximate each other, because I mean these matrices don't even have the same size, but we want that this outer product approximates this outer product. So this D by D matrix approximates this D by D matrix. For those a bit more familiar, specifically we need a spectral approximation, right? We need H tilde that spectrally approximates H in the following sense. How do we do that? So luckily this idea of spectral approximation is kind of established and people have looked at it, and there's this idea of sampling constraints or rows or data points via statistical average scores. So if you look at row I, then its statistical leverage score is essentially this quadratic form with in the middle A transpose A inverse, right? This A transpose A You can think about it as the Hessian that we care about. That kind of directly raises the following issue, that this is a chicken and egg problem, right? We want to use this idea to invert A transpose A, but in order to compute these leverage scores, we need to know what A transpose A inverse is. So that seems like a problem. So what you can try to do instead is you do something much, simpler, much dumber. What if you just uniformly downsample this? You just, pick a bunch of uniformly random constraints. What happens? Now, it's not so easy to see what happens, but luckily there's some very smart people, namely Cohen, Lee, Musko, Pang, and Sitford, who in 14 looked at that, and they showed that by somehow doing this uniform subsampling, you can at least learn something about the matrix. And in fact, by combining this with a bootstrapping scheme is a fancy word, you get an algorithm, that does leverage score sampling, that gives you this A tilde. And we combine their ideas essentially with something as simple as Grover's search, right? By using their ideas, we're kind of able to identify, what are the important constraints here, and in sublinear time we can find these using Grover's search. So what does a quantum algorithm do in the end? It returns this A tilde with only O tilde D rows, where n could be much larger than D. We end up with just O tilde D constraints, which is a spectral approximation, and the complexity is something like square root n D row queries, right? It's somehow the complexity of finding D important constraints among n constraints. This generalizes the idea of graph sparsification, right? If A is somehow the edge vertex incidence matrix, then this entire idea of spectral approximation is really just graph sparsification. So it generalizes this work together with Ronald DeWolf from 19, where we do a quantum speedup for that. It has applications in regression. I think this was just maybe 2 or 3 weeks after our paper came out. There was this paper that used this quantum algorithm for regression. And I'll just mention that for IPMs, interior point methods, we actually need additional work. Like this A matrix will generally be a rescaling by leverage scores or by Lewis weights, so we have to compute these as well. Okay, that's spectral approximation. Then we turn to the second component, which is approximating the gradient. Okay, so a typical gradient, I already mentioned that, looks a bit like this, right? We have this long matrix. We flip it, we get A transpose times the all ones. Now, if you squint at this from the right angle, this is essentially equal to the expectation of n times a random constraint. Okay, so what can we do? We can do quantum multivariate mean estimation. So again, this connects with the previous talk. There's this triplet of rising stars, Cornelissen, Hamoudi, and Yerby in 22, who proved that you can approximate this expectation, this gradient, this expectation using a number of samples x, where x again is just a uniformly random constraint, right? So it's easy to sample, using square root d times trace of the covariance matrix. So what does that look like? The gradient g is this thing here, and the covariance matrix is kind of easy to bound by n A transpose A. So A transpose A again is the Hessian. Okay. Filling this in, we get square root dn trace A transpose A. Seems not so great, because in fact this trace A transpose A again introduces a condition number dependence, right? It introduces dependency on the eigenvalues of the Hessian, something that particularly we did not want. Okay. And so here comes the thing that I think is one of the nicest things about this work, at least let's say one of the things that we're most happy about, the following idea that, remember that in the first part, we showed how to construct this spectral approximation, A tilde T, A tilde, of A transpose A, right? And what we can do now is we can use that to precondition our random variable. So that essentially we want to put this covariance matrix to be, proportional to the identity. And indeed, if we have this written out explicitly, so we can just sort of rescale this random variable, and then we end up with a random variable such that its covariance matrix scales as n times the identity, and we can sort of compute G out of it. So this results in an algorithm that just takes D times square root n samples, right? So this step is slightly slower than the spectral approximation, which was square root D square root n. Okay, but that's the main idea. Now we can put these things together to get a quantum linear program solver based on IPMs. So what it does, it explicitly returns you a solution x tilde that is feasible, right? It satisfies these constraints and is epsilon close to the optimal. And as complexity, if we look at sort of the query complexity, how many constraints do we have to query? This is like the main object that we care about. This is the number of steps of the interior point method times the cost of the Newton step, which is, if we use this very complicated Lewis weight barrier, it's square root d log 1 over epsilon. That's kind of the best that we can do in terms of number of steps. And the cost of the Newton step, because we have to take care of these Lewis weights and so on, we pay a bit more in the d factor here. We get square root n times e to the 2.5. Similarly, the time complexity scales as square root n log 1 over epsilon, and then this poly d. Okay, so notice that it's important that we turn to this most complicated recent Lewis weight barrier to get just a square root n dependency, because somehow every Newton step will have this square root n dependency, so we cannot afford this n dependency in the number of steps. Okay, so then I'll wrap up. So I presented a quantum interior point method for solving LPs without condition numbers. The runtime for n much larger than d scales as square root n poly d log 1 over epsilon versus the sort of n times d times log 1 over epsilon classical. We introduced new tools. We use the Grover search to construct these spectral approximations, and we use quantum mean estimation to approximate a precondition gradient. Finally, the main open question is, can we match, can we bring this down, like this d dependency essentially, to match this lower bound, which we believe is tight. So thank you.
Thank you, Simon, for this very nice talk. We now have some time for questions.
So this takes place in, like, we want to design sublinear, because classically, algorithms are so good, you can do it in near linear time, right? So we want to design a quantum algorithm that works in sublinear time. So we're assuming that in some sense we have a query access to, and what do we need in terms of query access? We just need to be able to ask, what is the ith constraint, which is going to be a small d-dimensional vector, right? So for every I, we need to be able to, ask what is the ith constraint. Either this is some oracle setting or there's some succinct representation of the constraints. But that's kind of the main, access model that we need. Okay. Mm. Yeah. Okay, so about the first point, choosing the initial point, that's a very valid question. Thanks for that. And it's something that people classically also have to deal with in path following methods. So there's different ideas here. There's one idea that somehow there's a way of finding this center point. Approximately, there's another idea of inverse path following, which is somehow you take a different point, you kind of you pick a random point, an arbitrary point inside the polytope, a feasible point, and then you can define some linear functional so that it's the optimal with respect to that. And then you kind of do inverse path following, right? So you have a different point, you trace back the central path to the center, and then from there on you kind of go towards the true optimum.
So you would do that classically, but you could also envision maybe having a quantum.
This is quantumly. This would be quantumly as well. Otherwise, we would pay the price as as a classical IPM method. Yeah. The second question was about, okay, if it's over constrained, okay, we're assuming that it's a feasible LP.
Okay, that's an assumption.
Yeah.
Okay.
Yeah.
You.
Thanks for the nice talk. I just had a question about the stability of the method. Have you looked at the stability?
Stability in terms of number of errors?
Yeah, there are lots of approximation that you're taking.
Okay, no, I think this is, I'm quite comfortable about that, let's say. Like, the idea is that somehow it seems tricky when you get close to the boundary, right? But then we're somehow what these interior point methods do and what these Newton steps do is they kind of, in some sense, look at the local geometry where you make things more smooth around that point by doing this rescaling with the approximate Hessian, right? And that means that all the approximations, like we're using an approximation of the Hessian, we're using an approximation of the gradient, and you can prove that that's enough. So we can afford errors in that, and I'm sure if you would say that there's additional numerical errors showing up, then there would be a way of dealing that just as you can do classically.
Thank you.
I just wanted to ask a bit about the computational model. So one query gives you back all the D numbers in a row. That's a row query.
However, yes, sure, that's where would be a row query, yes.
Okay, and do you need otherwise QRAM for your intermediate computations or not?
I mean, I think, like for instance, in quantum mean estimation, you want to have sort of quantum samples, right? So you need to store this approximate Hessian, which is d-dimensional, and do it, d-dimensional matrix vector multiplication. But I would say that all QRAM things would be scaling with d. So you could also remove QRAM, make this all explicit, and you'll pick up maybe a d squared, right? And so I would say this algorithm works in the circuit model if you want. You still have the square root, and if you can make the queries, right? If you can make the queries, it works in square root n. But just the d would be a bit worse, yeah.
Thank you.
Okay, so just one quick question. So if you wanted to match this lower bound, so do you need the improvement? Okay, I guess maybe depending on my understanding is correct, you only need it when you approximate the gradient? Like the spectral approximation is fine?
No, because the spectral approximation gives you square root n d, right?
Oh.
So that seems fine, but we need to do that square root d times.
Oh, okay.
And let's say if we just focus on that part for a second, then already kind of also classically somehow there's no way of getting this near linear runtime because you have to do that many iterations, and every iteration naively requires you to re-examine the entire input. So what classically people do, this is a very kind of hot topic now, is using these dynamic data structures, right? You change eta by a little bit, so the optimization problem, the new optimization problem you have to solve also only changed a bit with respect to the previous one. So somehow you have to reuse information from the previous iteration in the next iteration to not apply, to not pay again the full price. And I think this is one of the nice like new things in quantum, like this use of dynamic data structures. There was some paper last year at QIP, and this could use ideas like that as well.
Okay, thank you.
Hi, I have a naive question. So you were approximating this n-dimensional vector A to a lower dimensional vector A tilde.
Yeah.
And you were doing this because these are of different dimension. You said you were approximating based on the outer product.
Yes.
But I'm curious, this is a naive question. I'm curious, the outer product is also of different dimensions, right?
The outer product is not of different dimension. The outer product are of the form AI transpose AI or AI transpose of a d by d vector, but a sum of n of these. So you take a large sum of d by d matrices. So the resulting matrix is still d by d. And what we're doing is we're sort of sparsifying this sum. We're taking fewer constraints. So we're summing fewer d by d matrices.
Oh, okay.
Okay.
Thank you.
Hi, could you explain a bit more about the Grover search? Like how do you, just with the row queries, approximate the spectral matrix?
Sorry, say it again. How do we use it?
So you just use row queries to get the new approximation, right? Or do you use any other information from the original matrix?
No, we're using, so this idea of Cohen-Lee, Musko, Peng, and Sitford is somehow you kind of, you bootstrap in the sense that you uniformly subsample and gives you a bad approximation, not the one that you want, but you can still use it to kind of sample slightly smarter. And so you use this bad approximation to approximate these sigma i's, not greatly, but well enough so that you can then sample a bit better, and then you kind of keep on repeating that. And so you use these bad estimates of statistical leverage scores to somehow mark, based on these, which rows are important. This gives you the marked element oracle for Grover, and then you run Grover on the rows.
Thank you.
All right, let's thank our speaker once more.